technology, and he'll be going into that into more detail in adaptive and smart traffic management. So please join me in welcoming Steve.
So it's just-in-time scheduling here. I actually was at the room downstairs. I finally figured out I was in the wrong place. So my group has been working in the area of what we now call smart traffic transportation infrastructure, focusing on urban environments in particular. And I think some of you in the room know we started out and continue to focus on the problem of real-time adaptive traffic signal control. So, and that technology, as mentioning, is spun out and into a company, and we're starting to push that out into the other cities. What I was going to talk about today is sort of the work that we've been doing the last couple of years now, focusing more specifically on the opportunities that are being presented by the emerging connected vehicle world and connectivity, that the prospects of being able to talk directly to vehicles, actually pedestrians, anything, to talk directly to the infrastructure and what can we get out of that. So that's kind of what that'll be the sort of meat of what I'm going to say, but is what we're doing, looking at in that area. But so here's the outline of my talk. I'll start out by just sort of giving you a sense of the urban traffic control problem we've been focused on, and why SureTrack we feel is really focused, is really kind of a unique technology in that space. Then I'll move to the sort of work that we've been doing more recently, called here enhancing mobility with connected vehicle technology. And I'll talk about a number of different ideas that we're pursuing in that direction. And then finally, I'll sort of try to take a broader term, a longer term look at what I see the vision of smart infrastructure in the future. So let me start out. I'll just start out with one slide that sort of has motivated our work from the start, to just kind of give you a sense of the point. I mean, if you look out, particularly in urban environments, the intersections, the traffic signal intersections are probably the most unintelligent piece of technology you find on the street. And particularly in urban environments, the unintelligence sort of leads to sort of unnecessarily disrupting traffic flows. I've got a couple statistics here. These are already outdated. I sort of continually update this slide every year. A new mobility report comes out and the numbers get higher. But the ones I'm quoting here is sort of, you can see the magnitude of congestion costs to U.S. cities in terms of time and fuel. Another study, a recent study, indicates that drivers on surface streets in urban areas spend 40% of their time idling in traffic. So it's not a good situation. And a lot of it stems from the fact that, by and large, traffic signals are programmed for average conditions. A traffic engineer will go out for a day or two, measure volumes, get a snapshot of what the road conditions look like. And then on the basis of that, they'll build a fixed timing plan, a plan for allocating green to different directions of the intersection that optimize that snapshot. And there's a couple problems with that. One, actual conditions vary greatly and very greatly from average conditions in any particular setting. And moreover, they change over time. We started pilot testing in East Liberty, a couple miles from here, several years ago, and if I could look at the change in that environment over the last 5-6 years, it's amazing. It's going under revitalization, but it's a constantly a changing environment with changing traffic flows. So, in recent years, cities are recognizing that when they rebuild intersections, they're recognizing the advantages of newer technology, and they often will put in above ground detection now. But in point of fact, these sensors are really used the same way they were used 50 years ago. They're not exploited in any, figuratively speaking. You point cameras down to the crosswalk and you detect vehicles that are stopped at the intersection already. What we want to do is sort of look ahead, detect vehicles before they get to the intersection, and so that they maybe don't have to stop. So that's kind of the backdrop of what we focused on. We started out, I guess, in 2010 with some seed funding from Traffic 21 and Henry Hillman, and we really got a push on that sort of idea he had to try to improve traffic in the region, and we've gone from there. So the system we've evolved is a system called SureTrack, stands for Scalable Urban Traffic Control. It's unique in that, well, our focus really in designing the system was really real-time optimization of urban road networks. At least in the U.S., I mean, adaptive signal technology is not new. It's been around since the 80s. But at least in the U.S., it tends to be deployed principally in what you might think of as suburban corridors, where you're sort of have a main drag, you're running, maybe there are malls on the sides, and so there's clearly a dominant flow, and the role of the system is managing traffic on the side streets. What we're focused on is really solving a more complex problem, one where you have multiple competing flows that change through the day, like grid networks and so forth. So you can't really count on knowing what the dominant flow is at any point in time, but you really want the system to discover it and rediscover it through the day as things change. So we take a fairly, non-traditional kind of approach. We treat the problem as a collaborative online planning problem. It's sort of an approach that in my lab I've looked at it in various domains, but fits very naturally in the traffic signal setting. So the system is totally decentralized. Each intersection controls its own local traffic, watches through some kind of sensing, and makes decisions on how to allocate the green to service that traffic is seeing through its sensors. And then intersections communicate with one another to actually achieve network level coordination. So they share, I'll give you a sense of that. So in the field, we've started out, built a network here over time in Pittsburgh. These are the kinds of reductions that we get, and we're continuing to see them as these kinds of improvements as we move to other cities. I think I hit that by mistake. We tend to see reductions in travel times of around 25%. And it's not really because we're moving traffic faster. This is kind of a point that we really had to make to particularly pedestrian groups and bicyclists, and that we're not really moving traffic fast, or traffic's not moving faster. It's just stopping fewer times, and it's idling. When it is stopping, it's idling very few times. So I'll come back to this in a minute, but in 2015 we spun out a company, Rapid Flow Technologies, to commercialize the technology, and I'll give you a little sense of that. But let me just give you an idea real quickly of how it works. At the beginning of it, we put a computer in every intersection, and that's what I've called the intersection computer in the middle of this diagram here. It watches, okay, so that system's watching traffic. In this case here, we're looking at a video camera feed. At the beginning of every planning cycle, it pulls in information from the detectors that are watching the traffic, and then in real time, builds a predictive model, first of all, of when traffic is actually going to arrive at the intersection, or we expect it to arrive, and then based on that prediction, it generates in real time a timing plan, a plan for allocating the green to different approaches, and that matches that that prediction. So that once it builds a plan, it starts to send commands to the hardware controller. That's the device that actually drives the traffic signals. And but then it also communicates to its downstream neighbors what traffic it expects to be sending their way. So downstream neighbors doing the same things, building its local plan. But now, in addition to what it can see, what the traffic it sees through its local sensors, you can also see what's coming down the pike behind it. So we can build a longer horizon plan. And then this planning process repeats for each intersection every second. So constantly updating the plan. We're executing in rolling horizon fashion. But the fact that we're generating plans so rapid, repeatedly, so rapidly communicating information, even though we're talking just to our direct neighbors, even though an intersection only talks to its direct neighbors, information will propagate through the network in the way you'd like it. So as it gets further out in time, it gets less certain, but you do get this sort of network level communication.
So you said are you taking questions?
Yeah, sure.
Okay.
Sure.
You mentioned some statistics about reductions or improved efficiency. Where is this? Are these these are deployed up in East Liberty or near
Yeah.
like Penn Avenue or?
Yeah, I'll show you a map
okay.
in just a second. Up around the Target is where we started. Yeah.
Around Target, okay.
Yeah.
How many intersections are actually operated under your complete control at this point?
Right now, 50.
50?
Yeah.
I don't think I've ever hit one of them because I'm just so frustrated. But especially if you're driving around at a time that's not a rush hour.
Yeah. No,
You're just sitting there and there's no car coming the other way. I count the cars. Oh, no, that time nobody came, and I'm sitting here waiting. It's so frustrating.
Yeah.
But
Well, that's everybody has that kind of story.
Yeah.
We probably, well, you're technically correct. We haven't been running for the last month or so. We've been upgrading. We're upgrading the entire network. But
Okay.
we've been consistently running that network
Okay. Well, I'll wait
for 5 years now. So
I'll
I'll give you an email whenever we turn it on again, and you'll notice. Yeah.
Since he interrupted you.
All right. Sure.
Behind him. This is absolutely incredible. We just had a meeting over at the Tepper Quad about automated parking and finding our first site. They have to go to East Liberty now after watching this. Fantastic results. Can you actually determine the queue when cars are stopped? How many cars, whether it's 7, 10, 12, or are you just looking at a snapshot right through the intersection? Can you actually see the queue of cars waiting for the signal to change?
No, we're definitely modeling the queues, and I mean, we don't have ubiquitous sensing. We will as the connected world comes along, but we do, we do look outward with the cameras. I mean, essentially the way detection works is you define zones in the field of view of the camera. Okay. And so we'll have some looking right down at the crosswalk because we'd like to notice vehicles when they enter the intersection, when they leave the intersection. But we also have them in advance. And since we're doing urban, in a tight urban network, as a vehicle leaves an intersection, we detect that, and that becomes the advanced detection for the next downstream intersection. So I mean, we're not exact in the queues, but we do the best we can at sort of from the different snapshots that we get of building a model of that queue.
None of these cars have any kind of intelligence that you can...
Not yet.
So none of the cars have some kind of...
Not yet, but that's what I'll talk about later. That's the kind of thing we're exploring now, and that'll make a transformational difference in sensing.
Thank you.
Yeah. So some of the advantages of this approach, we're optimizing the signals for the actual traffic that's on the road. That's what we're doing. We're solving. We sort of think of it internally as a single machine scheduling problem, and we're trying to push all the jobs, all the vehicles through the machine, the intersection, in the most efficient way possible. So we coordinate for networks, not just arterials. We certainly can deal with arterials, but it's a special case. We're really solving the more general grid network problem. Since we focus on urban environments, we also optimize, what I've said here, optimize for multiple travel modes. When we first deployed, truth be told, we were thinking about moving vehicles, but as soon as we got out there, we did realize there were pedestrians out there as well, and sometimes very vocal. So we've spent a lot of time actually since then, paying attention to that, and so we're very interested in the ability to detect modes of traffic, and we can do that to some extent. Pedestrians are hard right now, but we're getting there. But if we were able to detect that, then the core optimization technique is capable of weighting different modes of traffic differently, or even if you're not weighting them, even if you're weighting them all together, if you have a dominance of say, I don't know, traffic moving through, or pedestrians moving through an intersection because the busway just dropped off a bunch of commuters, that'll be noticed, taken into account. The final thing is, since we're decentralized, we're inherently scalable. We're city scale. There's no central planning bottleneck. We pull information back to a traffic management center where you can view the traffic and maybe adjust parameters of the system, but actually all the planning is happening at the intersections, at the edge. So not only are we scalable, but another sort of attractive aspect for some municipalities is that you don't have to make a massive investment all at once. You can start with maybe a pain point, a pilot of 10, 15 intersections, cruise that out, and then sort of grow. That's how we've done the network in Pittsburgh as we've gone out. So here's what it looks like on the field. We've put a computer in the cabinet at the intersection. Our computer is the device at the very bottom there. That's an early version, an older, but it's basically just a weather-hardened commodity computer that it's nothing special. But it does have higher horsepower than the hardware controllers. We've not yet gotten to the point with the hardware controller technology where they can run fast enough to run our system. But there are actually detection companies that are putting computers in the cabinet now too. So there are opportunities. There's a lot of computing equipment that's moving in there. So it may be that we could be on board somebody else at some point. Here is the Pittsburgh network, the 50 intersections that we're currently controlling, which sort of run from the city's border with Wilkinsburg on the east, through Bakery Square area, East Liberty, and then into Oakland. But Pittsburgh, the city of Pittsburgh, going the wrong way here, has funding and a plan to add 150 more intersections. Our deployment right now is up in the right corner there, but they have this smart spines concept for which they've received federal funding, and that'll, I think, it's sort of mired down in contracts right now, but I think in the next 2 or 3 years we'll see that. Actually, when you get it, then at that point, having maybe a third of the intersections in the city, and most of probably all of the East End maybe, then we really have the opportunities to do some of the more advanced kind of things that I'll be talking about in just a few minutes. As I said, Rapid Flow has been focusing on broader employment, and currently live in 5 cities. We have 6 new cities that we'll be going into in 2019, and then we're talking with a dozen or so more municipalities. So we're starting to make it get the technology out. On the research front, we have I have a couple students who have PhD students who've been working on various kinds of extensions and innovations to this general approach that we call schedule-driven traffic signal control. So my one student, Boucher, who is defending next week actually, has focused on a problem of improving network level optimization by exchanging more and more information through, or different kinds of information through the network. So for example, I told you that sort of in the basic system, we push expectation of what traffic we're going to be sending to our downstream intersections. Well, now we also will send an intersection will send a kind of an indication of its current congestion level to its upstream intersections, and we can use that kind of information to provide kind of like queuing theory kind of guarantees of stability, that our queues won't and give us a transition to sort of move into a queue management when we really, the network starts to get saturated. So that's been fairly helpful. And then a second student of mine, Rick Goldstein, has also looked at extending the kind of search that we do under the hood to a higher fidelity model where we're looking at individual flows and individual lanes and movements, as opposed to some of the simplifications we made in the first approach. So I'm not really going to spend too much time with that. I wanted to get to the other stuff. So what we've been really a large part of our focus in the last couple of years has been on integrating this particular kind of signal control, real-time adaptive, with the connected vehicle technology that's coming. For those of you who may not know what I mean, or may not have heard that term, these are radios that they expect to be putting into vehicles that will allow the vehicles to communicate directly with other vehicles and also with the infrastructure. So the basic idea, or the basic motivation is safety. If you imagine two vehicles, the basic function will be every tenth of a second, each vehicle will broadcast a message that says, here's my location, here's my speed, here's my heading. And so if two vehicles are close to each other, or getting too close to each other, they might notice that, alert the driver that, or maybe just autonomously take.
Are they a radio signal or what?
Yeah, I mean, there are a couple. The technology we're experimenting with is called dedicated short-range communication, DSRC. And yeah, its main feature, its primary feature is low latency. It guarantees you a fast communication. And so in our Pittsburgh, our East Liberty deployment, or actually bomb center corridors, half of it are equipped with these DSRC roadside units that give us a test bed for experimenting, and actually our deployment in Atlanta also has these devices deployed as well. In the longer term, if you imagine a future where everything's connected, or by and large, all vehicles are effectively connected or have the capability, then the sensing we'll get will be so much better than what we have now. We can throw away the cameras we have, the radars or whatever we're using now, which are basically giving us snapshots when vehicles move over a certain spatial area. Here you'll be getting continuous information about where all the vehicles are on the road, and perhaps even where pedestrians are. There's a fellow here in ECE working on connecting bikes to, with these radios. So
are these is the proposal that like these being I don't know what the right word is. They're not privacy invasive.
Yeah. There's an anonymity that
it just says I'm a vehicle of this size.
Yeah.
In this location.
Yeah.
Moving in this direction.
That's right. Now what we've been that's true. What we've been looking at are circumstances where you may want to expose your identity. to your benefit. But I'll go along and you'll see what I mean. But yes, they're inherently in protecting your privacy. So this yeah.
I missed the first few minutes. Are vehicles weighted differently, like the school bus or?
That can be done. That's a possibility. We leave that decision to the that's a policy decision. So what we do is give municipalities the ability to decide what to do. Some of the work I'm going to talk about is aimed at sort of facilitating buses and things like that.
Public transportation.
Yeah. Emergency vehicles. You know, there's a lot of classes. So this future, I guess, you know, at the same time, it's still, I think, you know, decades away before you have that kind of penetration. So what we've been looking at is there anything we can do in the shorter term, in particular to enhance mobility. So we certainly support safety applications. That's no question there. But is there something we can do, or are there anything we can do in the shorter term to enhance mobility? So it turns out there's some pretty simple things that could have some pretty big impact. One of the ideas that we've been pursuing is what I've called route sharing here. The basic idea is really simple, is that if you are, as an equipped vehicle, are willing to share your route with the infrastructure, you know, like say you're using Waze or you're using Google Maps to direct you around, if you can imagine that being plugged to or that information, that route being sent to the infrastructure, then we've been able to show that we can immediately move you through our network substantially faster. You know, even at like 20% faster. I think that's where the blue line starts there, at the low level of penetration. So, and it doesn't really adversely affect vehicles or traffic that aren't equipped. You know, at first, maybe it sounds too good to be true, but it's really pretty simple. That you're giving us more information, reducing the uncertainty. You know, we don't have to guess if you're going to turn left or go straight at the next light. You've told us what you're going to do, so as long as you stay with your route, we can take advantage of that. So we have more information. We can do a better job of optimizing. And the interesting thing is, if you look at this sort of graph, you can see sort of this movement upward to the right. We're tracking sort of. This is a simulation study, but it kind of gives you the result, the idea. The blue is tracking the sort of equipped vehicles, and then you've got all the average of all the traffic, and then even the ones that aren't equipped. So you can see that after a certain level of penetration, everybody's performance is going to rise. What you might expect. I mean, as you get better connectivity, just like we were saying, better sensing, you expect the performance of the network to rise. But it also sort of gives incentive, or you think about giving an incentive to be an early adopter, for example. So suppose you're a first last mile freight company operating in the city. You know, if you're willing to equip your vehicles, we can move you through. We can improve your operations quickly. Municipalities have various fleets of vehicles. You know, you know, ride-hailing companies, Uber, Lyft, they all generate their routes from central locations. They know their routes, so if they would give us that, we could again improve their operations. So yeah.
Do the sensors need to be built into the vehicle, or could you just plug something?
Yeah, I mean, the idea originally, I mean, the real idea is that eventually they will become part of the vehicle. There was a time in the U.S. where it looked like the government was going to mandate that all new vehicles would have these radios, kind of like a seatbelt rule. But it's not so clear that's going to happen now. But the industry is moving forward with it. There are several car manufacturers that have production models that do have a radio in, but you can also buy them as aftermarket, you know, and just, well, when we experiment, we just put them, you know, we just buy one and put it in the, on the dashboard or something, you know.
How expensive, how cheap do you think you could get a device like that and sell it?
It's a good question. I don't think they're cheap enough for the, certainly not to get into cell phones yet, the chipset, but right now they're about $700, something like that. Yeah, yeah. But you know, part of it is that the vendors don't know what to do because you know the government, and there's this sort of beta versus VHS debate going on with 5G and what's going to, you know, some companies are going in that direction, so it's not clear exactly who's going to out. Yeah.
Have you approached ways about just purchasing their de-identified data off existing accounts rather than having to get an opt-in?
Well, that's an interesting question. No, we haven't actually pursued that, although we have talked with Lyft about just getting some of their data, just as this is kind of a preliminary step, just to kind of say, well, look, give us some data of your historical trips, and then we'll plug it into one of our networks with the, you know, the rest of the volume information, and see how much better we could do in simulation, you know, that kind of thing. But no, we haven't done that. We had some conversations with TomTom, which is bigger in Europe, but also have a lot of data like that. It's an interesting question, but we're also, I'm just going to save this till the end, but we're also thinking a little bit different about sort of in a longer term vision that maybe kind of a tool or a tool like this could be used to create a more sustainable approach to infrastructure. What I mean by that is really sort of some kind of a voluntary tolling where you pay a small price to go through the intersection in exchange for getting expedited. And you know, you could actually create revenue stream for a municipality out of that, and sort of make you know, in the very long term, as the world gets more and more electrified, the federal gas tax is going to be less and less. You know, that's kind of what funds the infrastructure today. So anyway, but you make a good point. I mean, there are a lot of different ideas that we could think about. And that one makes sense. I agree. So anyway, this is one sort of idea that we're pursuing. We've actually just started a collaboration with one of the self-driving car companies here, Argo AI, to sort of look at. They're sort of interested in ride-sharing application. So we're talking about doing just an initial demonstration pilot in the field to see how that will work. Another opportunity that you could think of would be, as we mentioned earlier, the buses. Yeah.
That's it. My mind's just going crazy right now. If someone has a smartphone,
Yeah.
is there such a way that you can triangulate off of a satellite and you can match me up as a pedestrian with a smartphone in my pocket that you could talk to in your system? Or if I'm using Google, whatever I am, I'm a driver for Uber, whatever I am, that you can marry me up with that truck at that location going through that intersection at the time. Is there a marrying technology that I can identify based on my cell phone?
It doesn't. It doesn't exist yet, but I'm going to talk about that in a little bit. It's a good idea, or well, it's a controversial idea also. Some people don't want to, you know, be passively detected. But yeah, I think I think there will be a future where, you know, you can think of having these
location apps everywhere.
These radios embedded in a smartphone
and
so forth. So I'll get to that just in a minute. I'll show you some stuff we're doing in that area. But so transit's another area where you could think of, well, here's a fleet. We could equip the fleet. We always know the bus routes, so we could take advantage of that. But there's also other kind of, you know, even if we can just know a bus is coming and have a better picture of when it's going to arrive at the intersection, since they're big blocking vehicles, we can, have I think already have a significant effect on improving traffic. So we're working with the Port Authority, and the basic idea is to equip, at this point, is to equip buses that are moving through our corridors, actually Center Avenue mainly, and use that as a pilot test to test some of our ideas. So the first step is really just to kind of use location information to build a more predictive, a more accurate model of when the bus is going to get to the intersection. In the longer term, at least in Pittsburgh and I think many other cities, they have an onboard computer that has a lot of real-time information. They know how full the bus is, so you can start to think about moving vehicles based on how many people they're transporting and things like that. You can know whether it's on time or not.
I'm curious, how do they detect all of those? I can see automatically being picked up by pulse.
They somehow count, are able to count when, I don't know if it's exact count, but they are actually counting on and off.
They have detection. They have like a line as people cross that counts.
Okay.
Just to count
Okay.
It's just a basic query. Yeah.
Yeah. Okay. Okay. I didn't actually know how they did it,
That
but
just popped out as.
yeah.
It's not something used across all buses and the different prototypes that are used. So we currently made a choice to implement for Port Authority. So.
Yeah. Okay. But they also collect information on door open and door close events. So in Pittsburgh here we have like a lot of cities, we have near-side bus stops that don't have cutouts, so they block traffic while they're stopped. So, but since we're a real-time system, you could actually imagine maybe noticing the doors are closing, taking that as a signal that they're leaving the bus or leaving the bus stop, and and then being able to take some decision before they actually get to the intersection. So, yeah, I'm sorry, you had your hand up.
Oh yeah, no, I was just, this was actually going to be my question for the last slide. If there's a component that you're using, the existing routes,
Yeah.
in the route sharing space as well. And just on the note about capacity, I think Port Authority uses the CAT AVL system, which we in Chicago we use that as well.
Mhm.
The capacity was not very accurate real time, but things like bus delay and which would be great for optimization.
Yeah.
I was wondering if you were using the route component in the earlier slide that you showed as well.
Yeah, well, we haven't done that yet, but that's part of our plan. We can pull that information from somewhere. It doesn't change basically. So yeah, we certainly would want to use that. What we focused on to date, while the Port Authority is configuring their buses, is what I think is the biggest challenge is predicting dwell time at the bus stop. And so I have a couple slides on that. I'll go through quickly, but of just predicting, how long the bus is going to stay there. And so we've gotten 2 years of data from the Port Authority, and we've spent some time looking at that data and come to some conclusions. And now we've developed. I'm sort of telling you my next slides here. Maybe I would just go. Well, anyway, just to kind of give you a sense of what might be possible, here is a simple simulation experiment we did with some data from a particular intersection at Penna Highland. And basically, and that one's a notorious one because it's the blocking, it blocks traffic behind it when the buses is stopped there. And this was a simple experiment that just said that a bus, to sort of mimic what you might be able to get with if the bus is able to communicate its arrival time in advance of the intersection. So what we did here was just a very simple experiment where we just assumed when a bus was at a bus stop that we just assumed there's going to be a fixed delay that would not get, this is not realistic, but it's just, there's going to be some delay. We just said here, suppose it's this way, and we force the traffic signal to go the other way. And you can see that, at least in the simulation results, that in all cases, both in normal volumes and high volumes, the average travel time improved for both the vehicles and the buses. So there's a lot of opportunity here, and as I was saying, the challenge really, I think, is doing a job short of being real reactive, real time on the bus doors, is to be able to predict the dwell time of buses. So we spent some time. We looked at 2 years of Port Authority data. We looked at the two main bus routes that move through Center Avenue, 71A, 71C, for those of you who know the areas. And you know, we got a lot of different information on these, and as I said, about 2 years of data. What we found was, that there are some repetitive things. We do see strong seasonal correspondence in dwell times from year to year, but we also see that dwell times vary, as you'd expect, I think, considerably by stop, and that they also vary greatly within peak periods. So, you know, there's so the implication here is that your sort of standard regression models are not likely to be too effective here. So anyway, a colleague of mine, Isaac Isakpati, has developed, working with some students here, and developed an accurate probabilistic model of bus dwell times that sort of is distinguishing on each bus stop and each bus route. You know, it's interesting to note, I guess, maybe it's not interesting, but you know, you know, the world, deep learning is going to solve all the world's problems. But this is not a big data problem, because you don't really have a lot of contextual information about that would allow you to distinguish. So what you really want is a predictor that's going to get accurate with minimal amount of training, and you can just do it online. And that's sort of the approach we've taken here. You know, the actual approach we're using is a hierarchical Bayesian net formulation. But we found that it allows us to get pretty accurate predictions, you know, in just about 20 data samples. And so the technique that we're using, that sort of every time it gets a new bus arrival, it sort of updates this model, and it sort of is rolling, you know, really with the real-time and recent historical information. So I got some numbers on the side there for different bus stops, but basically what these results show, that sort of consistently this kind of technique, which is labeled FISC in the table, will outperforms the sort of standard linear regression kind of model that one might use. So our current status here, I think I already mentioned this, we have this dwell time model now integrated into the predictions that SureTrack makes when it's sort of predicting vehicle arrivals at times at the intersections. And we use that prediction to sort of alter where we, you know, to propagate the implications to both the buses and the vehicles that they were going to block. So we have a model that, you know, depending on how many lanes, we'll sort of understand how the flow is going to get disrupted. We've I guess last year installed a DSRC onboard unit on a single bus, and it turned out to be a pretty simple install, and we successfully tracked it through our corridor. So that those videos, or those visualizations on the right, are sort of real time watching the bus move through the center. The Port Authority, we're waiting for them now to order. I mean, their plan is to equip, I think, 50 buses, and that'll be all. That won't be all the buses that move through that corridor, but it'll be the main, really the big. They call them the ones that have the articulated. Yeah. Yes.
Have you looked at trying to have, for lack of a better term, a big monitor connected to your computer that would give you real-time information when buses are due to arrive, even your signals, when to walk, when not to, as a pedestrian, something that could actually take the data that you're accumulating and give something that would be useful for people managing that intersection.
Yeah.
That are
Well,
sitting there
I mean,
waiting
that's
for
what
you
we're
to
trying.
walk.
That's what we're trying to do automatically, right? We're trying to, you know, we don't have a computer itself doesn't need to monitor, but you know, by getting this information in, making use of it right away,
Right.
that's what we're trying to do. We do provide sort of a back-end interface that, you know, and if we're using some kind of detection that, like cameras, you know, we can flow that stream back, and I guess it certainly would be possible to augment that display with more information about what's going on there. We try to compute statistics in real time to show how we see the intersection performing, you know, at present along with the visual feed. But yeah, that's a good idea. Yeah.
Do any of these intersections already have, you know, like when you allow pedestrians to walk, they're synced up with the traffic signal, you have a smart signal, I'm assuming you have pedestrians across these roads. Is there anything right now where you're looking at making those more than just a picture of somebody, but something that would have useful information, like I said, when the bus is supposed to come? The 7:36 is coming in 2 minutes late, or whatever. Whatever would be useful for people at that intersection.
Yeah.
To make decisions.
Yeah. Well, we're doing something like that. You know, it turns out there are apps out there like for the buses. You know, there's like a transit app that is pretty. People I talk to who use it think it's pretty good. You know, what we have talked about doing is, well, as part of this third project, of helping a particular class of pedestrians, pedestrians with disabilities, to sync up with buses. And so that's, even in that context though, we kind of think of that they would use, that we would interface with an app like they already use, like Transit, or there's some route planning apps.
I throw one more. You're killing me with this presentation. This is unbelievable. FedEx is coming out with a robot that goes 10 miles an hour.
Yeah.
Cross roads and deliver prescriptions
Yeah.
from all the retail drugstores, the shut-ins that are in their house, bringing medication or whatever they need. Are you going to be able to communicate with the FedEx robot that they're announcing here?
Yeah, I mean, they just have to put a DSRC radio on top, right? Yeah, new travel mode. Robot. Yeah, no, that makes sense. Yeah, I mean, a third project we're about halfway through with funding from the Federal Highways Administration is really sort of aimed at, well, a special class of pedestrians, but looking at essentially the concept is to build a smartphone app that would talk directly to the intersection and allow, I guess more importantly, allow the intersection to or allow active influence of the traffic control decisions. So the most basic idea, is that the phone or the app would know your personalized constraints, know how fast you travel, for example, and use that information to communicate. You know, when you communicate intent to cross in a certain direction, you can also, you know, you have to communicate how much time you need. And so that when you do get the crossing signal, you'll have enough time. You'll have enough time to cross. You know, interesting. This is diversion, but I don't know if any of you see those push buttons on. You know, no matter how many times you push it, it doesn't bring the light to you any faster, or the crossing to you any faster. I never knew that until I got into this. But what it does do, though, is that it notices that a pedestrian's waiting, and when you do get to cross, it'll maybe give you more time than it would have otherwise, just to make sure you have enough. Here, we're specializing that even further, taking the push button out of the play for these individuals, and also using their speed.
I'm just curious, when you make a road like Center Avenue more efficient, do you then see more traffic coming that way? Because
it's a good question. I mean, I think that's sort of classic phenomenon that you see in capacity studies where you build a bigger highway and you get more traffic and all that. I guess that to some extent that's true, but I know the first couple of years we were in East Liberty, we tried to pay attention to that to see what that was, and we didn't notice really a big difference there in volume. Volumes were kind of stable, but yeah, I think there might be some of that phenomenon happen. When you experience, it's not like you're never going to stop. There is congestion, but you'll feel you're moving faster. But
I would
yeah.
avoid that area unless I would had a reason to go there. I mean, it's not.
Yeah.
I don't think it's a good way of shortcut anything.
Yeah, well, right. Maybe that's part of it too. That it's not really a throughway in a way. But yeah, I don't know. Yes.
How about from this? Everybody's worried about safety, Argo AI. Everybody's safety. Have you noticed any improvements not only in the cycle time, but the statistics are phenomenal? Have you had any reduction in fatalities or people getting run over?
We haven't done that analysis. There is a fellow at the Industrial Engineering Department at the University of Pittsburgh who had a student look at that safety issue. I don't know if it was crashes or what, but and I could point you to that. I have to look it up. I could point you to that paper. They found that it was safer. Their conclusion was that safety was increased, but I don't really know the details of it, and it's a really hard thing to judge, I guess. But we haven't really looked at crash data, so it's a good question. We probably should. There's that study, which I guess maybe they did look at some crash data, and I know a competitor company has white papers out about how adaptive control is so much safer. Yes?
Have you seen side effects of the system? Like if you control one intersection versus you control a neighborhood or city?
Well, yeah. I don't know about side effects per se, but I know when we first deployed and we tested at 9 intersections, and you could really tell that we were really constrained by this one that we didn't have right outside of our thing. So when we expanded it, we got that one in. But as far as pushing traffic to another,
well, for instance, if you only control one intersection, perhaps you can't control traffic.
Yeah. You really, that kind of is part of the, I think, art of picking. If you're going to pick a certain set of intersections, of defining ones that give you the best chance of having it dissipated by the time you're out of the network. But yeah, we were talking to a group. We are talking to a group in Beverly Hills, and their question was, "Well, are we just going to make Westwood's traffic terrible now?" And I said, "Well, then they can come to us." Anyway. Well, so getting back to this idea, so the other thing though is since the app would have localization capability, we could also track the pedestrians' progress across the intersection, and since we're a real-time control system, we could, in circumstances where we detect that they're moving slower than expected or such, we could dynamically extend the time. And then we're also looking at trying to do some of the same mobility ideas that we were applying to a vehicle. So if a pedestrian is willing to give us route information so that we can anticipate their arrival at the intersection, then we can fold that into our optimization and maybe streamline their trip. If they're they want to go to a couple blocks to catch the bus and then go to another part of town. We can maybe streamline that approach. So our approach, it turns out there's no smartphone that has a DSRC chip radio in it at present, but one of the vendors does make what they call a sleeve. That's the thing that's pictured on the right. I didn't bring it with me, but that white piece there is a DSRC radio. It has a sticky thing on it. You stick your phone on the front, and the phone talks to the radio by Bluetooth, and then the radio talks to the intersection with DSRC. So the approach is, so we're using that as our sort of initial prototype device. Actually, following our first year experiments, we're now also developing a cellular option. So we'll provide both options. Only because we think that might be a quicker way to get it commercialized. And since pedestrians, you know, I mean, the real advantage of DSRC is this low latency guaranteed response time, which is very important for vehicles, but since pedestrians move a little bit slower, you know, maybe it's not as much of an issue. So we've taken a universal design philosophy. We have, just because of the local population here, have focused, you know, in the prototype principally on accommodating blind individuals, but we really our goal is to provide a device that could support a number of different disability types. We have multiple interaction modalities. There's an interactive display. There's voiceover. We have some haptic signals. And we are actually using we're building it on an iPhone. This was actually kind of suggested to us by members of the community that you know, and I know they're a little more expensive. We'll probably go to a transfer to an Android kind of device at some point. But the very nice thing about the iPhone is it has a great accessibility features that you can take advantage of. So we're totally integrated with those. So we get the voiceover and all of those capabilities for free. Yeah.
You have a lot of bike lanes that are separated, but also a lot of behind traffic.
Yeah.
Complex and so things.
Yeah, no, for sure. Yeah, I mean, actually, it turns out that bicycles are one of the our mode of transportation that most video cameras can detect. We certainly do better when they have their own lanes, because then we can really sort of know that they move at different speeds and things like that, and possibly do a better job of integrating into the flow. Yeah, you know, no, you're right. Our model is actually at this point is not that sophisticated that we could change the, you know, we depend on parameters like free flow speed, things like that, but we don't adjust that in real time. We're not that accurate. But it's a direction we should probably go as we get more. Yeah. So I better speed up here.
About 1 o'clock.
Yeah. So this is just a quick video of how it works. Let's see if can I find it. It's pretty straightforward. You know, you're walking, you're approaching an intersection. At some point, the intersection is broadcasting messages, two kinds of messages: a map message that tells you the geometry of the intersection, and a spat message which tells you what the current phase is when it's going to switch to the next phase. So when you do come in range, you get a choice of crossings. User's already picked one here. He picked a future phase, so that the app tells him not to cross, and then as you get near the signal change, it starts to give you a countdown. And then once you are, it announces you're ready to you're okay to cross, and you know, it gives you a countdown. One of the, I'm not going to have time to talk about the field testing we did, but one of the interesting things we found out is that, which was a little counterintuitive to me, but it makes sense now, is that we tested our participants with and without the use of the app, and thinking mainly now of blind individuals. And I won't have time to show you, but it's amazing what the challenge is in crossing the street. You know, you're basically just listening to traffic and waiting. But what we found was that I sort of thought with the use of the app, they would get across the street faster. And I think that's true in terms of the number of cycles they wait through before they make the run for it. But it it turns out the opposite. Once they make a run, I think they just bolt across as fast as they can. And so, with the countdown going on and all that, they were sort of, one side effect was sort of they were, more comfortable and with, more relaxed, I think, crossing. I'm going to buzz through some of this, we're also doing some work toward using low cost sensing to do real-time incident detection. Essentially started out as a problem or a desire to self-monitor the performance of the network, so we wouldn't have to do physical drive-throughs to evaluate performance. We could just always know. But we're thinking, now that we have that kind of capability, we're thinking that we can use that to detect incidents in real time and make use of that. Let me just finish up here. So I guess what I'm, as we look at the future, this, I'm calling it X infrastructure communication to include people and vehicles. We see increasingly that the signal network, the intersection, is really going to become a gateway for real-time information, and there are lots of opportunities to sort of take advantage of this. And since we're on the ground there, we have sort of I think a better prediction of what's going to happen in the immediate future than Google Maps or at least in the short horizon. We're sort of on the ground there. And so there's a lot of opportunity, I think, in the longer term towards sort of providing guidance as the world gets connected to vehicles moving through. As self-driving cars come along, they're going to use the same kind of technology that we're experimenting with. It may not be DSRC, but there'll be some, connectivity to the infrastructure. I've heard several self-driving car companies or their talks talk about how the side effect will be no congestion, but I don't really buy that future. I'm not sure they do either. There may be less parking needs because vehicles will be circling all the time, or driving out of time to park. But there certainly will always be congestion, or that a need to sort of mitigate or we're up against that. So we may not need physical traffic lights if everybody's talking to everybody, but I think we probably will anyway because pedestrians and such. So I mentioned a little bit about sustainability. I don't really have time to go more into that, but I guess my bottom line is I think smart infrastructure is really a key to urban mobility. It's not the total solution. I mean, there's got to be it's got to be a mix of multimodal traffic and travel and transportation options. But it's certainly a big key. So I'll stop with that.
Thank you. All right. So I know many of you were very excited and intrigued by this. Just I don't know if you have some time to talk to folks who want to make a connection, but
sure.
Generally, to take some more food. Right, yes. There are a couple of us students who are going to be meeting for Transportation Club to talk about these topics and other topics. It's kind of where Taylor is, if you want to raise your hand. So we'll kind of divide the room that way, just so that folks will still have the opportunity to talk to you, and students will be able to gather better. So thank you very much for coming. These series are every 2 weeks. I think if you were able to check in on the URL, we'll add you to the list of announcing these talks. So thanks for coming. Thanks again.
Too much stuff.
No, for sure, definitely. I think talk about things, give you more of where we're at, give you wisdom that you heard today. But I mean, we're moving full steam ahead right now. The
that the April 6th thing at night?
Yeah.
Okay.
Yeah. So
That's awesome.
folks from Jordan says hi.
Yeah.
They're coming to stick around.
Yeah. This is yours, yeah. That's
Transportation programmer?
I am. You have migraines today.
I am not. I go to the internship.
All right.
No, don't worry about it. No, Mike does.
Oh, yeah. That's perfect. Hi, how are you? How are you? It's Friday. It's Friday.
Yeah. Well, that's the thing about that one.
Oh, right. Oh, well, we're good.
That's kind of why we think it's kind of interesting.
Sorry?
It is.
Oh, okay. I wasn't there last week. I was like,
We almost saw the
You said you were interested in buying, honestly,
yeah, like too bad.
I don't think about that. So maybe after the schedule,
yeah, sure. Let me know.
Someone will.
I don't, but I, okay, sorry, yeah. I'll send you.
Yeah. Oh, I could have.
You could have finished.
I was done 3 days ago. 4 days ago. I was done so early, and then except it was like plenty off. So I was like, "Sir, we're good." The last 3 days is my studying.
Yeah.
I appreciate it.
But you know, I
would have never found that.
That's why, yeah, sometimes I can't see it, and sometimes you pick it out. And picks it out.
Okay, you know, and it's like what? There's only one only line on that you're
Oh.
see like
you know, I can't really say that.
what's that?
One connected thing was replaced.
Yeah.
There's cool women in transportation.
That's something different how you're doing it.
Yeah.
Or how I had told you the first time.
Oh, and then
It may have been that we had, there may be.
Yeah, right.
Well, non-ordinary stations that were like
I mean,
covering up.
yeah, I mean that's why it's good to track. So, I mean, the more you get, the better.
Like, yeah. So, no, this is good.
I didn't know what was going on. I was
just had some data issues in Amtrak.
Miraculously resolved themselves.
I woke up to like 12 minutes. Also, Sarah, I'm scared of reading things I read. So, you know that?
No, I haven't.
Okay, so probably the varying learning rate part is
Oh, I see. Right.
Yeah.
So I think,
Yes. Yep. So he's actually going.
Marcus said he might.
Yep. I think we're all just kind of spread out.
Yeah, this is not a, like, this is kind of an awkward room.
Yep.